So welcome you to today's lecture. Do you have any doubts from the last lecture or any of the previous lectures? Okay, there are no doubts. Let me start with the next topic in the course. The concept of sufficiency. Basically, notion of sufficiency is about the reduction of the data. What we dealt with so far was sufficiency. Basically, there is a notion that deals with reduction or summarization of data. M-dimensional data, you can go up to one-dimensional data, depending on how much information your sample contains. Then we realize that in a given situation, there could be many sufficient statistics. All of them may contain the same amount of information. Then came the concept of minimal sufficiency. Minimal sufficiency is a notion which helps us. Okay, let me, I guess my. Yeah, any doubt anybody has? Okay, so minimal sufficiency was the notion about maximum reduction in data. Among statistics, or among sufficient statistics, you look for a statistic which gives you a maximum reduction in data. Now we are going to discuss about a notion which is very complementary to sufficiency. You see, sufficiency says a sufficient statistic is something which contains all the information. And a complementary of that statistic would be a statistic which does not contain any information about theta. And note that a statistic will not contain any information about theta, provided its distribution does not depend on theta. And that leads us to the concept of ancillary statistics. So this is a complementary of a sufficient statistic, in the sense that an ancillary statistic is a statistic which does not contain any information about theta, or in other words, a statistic T is said to be ancillary if its distribution does not depend on theta. So in certain sense, it is very complementary to sufficient statistic. So as such, an ancillary statistic does not contain any information about theta, in the sense that its probability distribution does not depend on the unknown parameter theta. Look at this example. Suppose you have a random sample from uniform theta, theta 1, so that v1x is equal to xn minus x1 and v2x equal to x2 minus x1 are ancillary. Now, this belongs to a location family. Location family has a PDF of the type f of x minus theta. So this would have a PDF f of x minus theta, where what is f? F is 0 if x lies between 0 to 1. One density as fx minus theta, where fx is 1 if x lies between 0 to 1 and 0 otherwise. So that when I write down f of x minus theta, What would be fx minus theta over in this case? This would be 1 if x minus theta lies between 0 and 1. So that means x lies between theta plus 1 and 0. So any density whose PDF can be written as f of x minus theta is called a location family. Now it is a family of PDFs because here theta is where theta is anything in R. It's not a one PDF, it is a family of PDFs. So any family of PDFs there was some problem. Did you hear the lecture, the previous part of my lecture?
So during the example, it went off.
During the
Example, that location family, you are telling all those things.
okay, so that much I have. Let me again do it. So location, when I say a random variable has a distribution belonging to location family, what it means is its PDF f theta x is of the type f of x minus theta, where f is some PDF whose distribution does not depend on theta. So f of x is 1 if x is between 0 to 1 and 0 otherwise. Similarly, we can talk about a scale family. A scale family is a family of distributions such that its PDF can be written as 1 by theta f of x. Fx is 1 if x between 0 to 1 and 0 otherwise. Uniform 0 theta similarly can be written as 1 by theta f of x by theta. And what would be your fx over here? Again, the same one. 1 if x lies between 0 to 1, 0 otherwise. So that when you use this f, what is f theta x? It is 1 by theta f of x by theta. F of x is 1, so you have to multiply it by 1 by theta, so 1 by theta. If x by theta is between 0 to 1, since theta is positive, that is equivalent to saying that x is between 0 to theta and 0 otherwise. So uniform 0 theta is a scale family. Uniform theta theta plus 1 is a location family. Normal theta sigma square, if your sigma is known, then it belongs to a location family. Exponential theta belongs to scale family, right? It is 1 by theta e to the power minus x by theta. What is normal theta? 1. 1 by root 2 pi e to the power minus half x minus theta whole square. So that can be written in terms of x minus theta. Exponential can be written in terms of x by theta and so on. Similarly, gamma is also a scale family. So what I'll show is, I'll try to see a class of ancillary statistics for a general location and scale family. So first let us look at, let x1, x2, xn be a random variable. It will be a random sample with common distribution function fx minus theta and PDF fx minus theta. So note that this PDF is of the type f of x minus theta. Let Vx be any statistics such that Vx plus C, Vxn plus C is same as V of x1, x2, xn. What it says, if in location family you are dealing with any statistic which is of the type V of x1 plus C, xn plus C is V of x1, x2, xn, or in other words, it is translation invariant or location invariant. Translation invariant means if you translate each variable by C, the value of the statistic does not. So in location model, any translation invariant statistic would be ancillary. That is what it says. Now, the proof of this is very simple because then you know that V of x1, x2, xn would be same as V of x1 minus theta, xn minus theta, because V of x1, x2, xn is same as V of x1 plus C, xn plus C for any C belonging to R. But x1 minus theta, x2 minus theta, and xn minus theta are IID because x1, x2, xn were IID. With PDF, what was the PDF of x1 minus theta? X1 had a PDF f of x minus theta. So what is the PDF of x1 minus theta? It would be f. So that means the distribution of x1 minus theta, x2 minus theta, xn minus theta does not depend on f. They are IID. So that means their joint distribution will also not depend on theta. So the joint distribution of does not depend on theta. Why? Because since the distribution of x1 minus theta does not depend on theta, so any of the xi minus theta distribution will not depend on theta. And what will be the joint distribution of x1 minus theta, x2 minus theta, xn minus theta? It will be the product of f of xi's. So V of x1, x2, xn has same as distribution as V of x1 minus theta, xn minus theta. But distribution of x1 minus theta, x2 theta minus theta, xn minus theta does not depend on theta. So the distribution of V of x1, x2, xn does not. So in the location family, any statistic which satisfies this condition will be ancillary. Now you can look at xn minus x1 satisfies this, because if you change each xi to xi plus c, then maximum gets changed to xn plus c, and minimum gets changed to xi plus x1 plus c, because each has been translated by the same factor. So maximum would get translated by the same factor, same quantity. The minimum would get translated by the same quantity, and because of a minus sign over here, that cc would get cancelled, and you again get xn minus. V of x1 plus c, xn plus c would be same as v1 of x1. So this is ancillary in the location family. Similarly, v2x, which is summation I is equal to 1 to n xi minus x bar whole square. This would be ancillary. Why? Because if you change each xi to xi plus c, xi becomes xi plus c. And if each observation is translated by c, the mean would also get translated by c. So again, here xi plus c and x bar c, cc would get cancelled, and you will get the same v2x. So this is also ancillary in the scale family. Now let us look at the example of a scale family. So let x1, x2, xn be IID random variables with distribution function fx theta and PDF 1 by theta, fx by theta. Let Vx be any statistic which satisfies V of c x1, x2, xn is same as V of x1, x2, xn for every c belonging to R. Need only for every c greater than 0, then Vx would be ancillary. How do you show that? Note that V of x1, x2, xn in this case, I can take c to be 1 by theta. So you can say that for every c greater than 0 only you need. If this happens for every c greater than 0. Let us look at V of x1, x2, xn. because V of x1, x2, xn is same as V of cx1, cx2, cxn. I can take C to be 1 by theta. It becomes V of x1 by theta, xn by theta. But what is the PDF of x1 by theta? x1 by theta, xn by theta are II. Because x1, x2, xn were IID, and I'm multiplying by the same factor 1 by theta. So they would be IID with PDF. If your x1 had PDF 1 by theta, would be the PDF of x1 by theta. So 1 by theta dx1 would go into Jacobian terms, and you get just f. Since they are IID, their joint distribution of does not depend on. And since V of x1, x2, xn is same as V of x1 theta, xn theta, so distribution of V of x1, x2, xn will be same as distribution of this. But here the joint distribution of x1 by theta, xn by theta does not depend on theta. The distribution of this will also not depend on theta. So in particular, distribution of V of x1, x2, xn will not depend on theta. So V would be ancillary. So in the there was some issue with the network. Let me again, the connection dropped down. Let me again start from where I left. So if I look at the statistics xn upon x1 to show that it is ancillary, what I have to show is if I multiply each of the observation by a quantity C, which is positive, then the value of xn upon x1 will not change. Now note that the maximum based on cx1, cx2, cxn would be C times maximum of x1, x2, x. So there are serious issues with the internet today. So when I look at statistics, when I look at V1 of cx1, cxn, it is maximum of cx1, cxn divided by minimum of cx1, cxn. But because C is positive, so maximum of this would be same as C times Xn. Similarly, minimum of Cx1, Cx2, Cxn would be same as C times X1. So Cc gets cancelled, which is same as Xn upon X1, which is V1 of X1, X2, Xn. So in the location, in the scale case, Xn upon X1 is ancillary. Similarly, X bar upon X1 would be ancillary. Why? Because if you consider the mean of Cx1, Cx2, Cxn, it would be C times X bar. And X1 has been translated to Cx1, so Cc would get cancelled. Again, you get V2 of Cx1, Cx2, Cxn as same as V of X1, X2, Xn. So it is ancillary. Similarly, U3X, which is X1 upon X2, is ancillary because when you translate each of X1, X2, Xn into Cx1, Cx2, Cxn, this becomes Cx1 divided by Cx2, Cc gets cancelled, and you get X1 by X2, which is same as V3 of X. So now we know in general how to find ancillary statistics, at least in the location and scale case. So recall that ancillary statistic is a statistic which does not contain any information about theta. This doesn't mean that ancillary, when used with something else, may not contain any information about theta. You see, as such, what it means is ancillary statistic in alone may not contain any information about theta. When ancillary statistic is used alone, it may not contain any information about theta, but there is a possibility that if ancillary statistic is used with some other statistic, it may contain, they together may contain relevant information about theta. And that is what is being explained in the next example. So suppose I have a random sample X1, X2, Xn from uniform theta, theta plus 1. Now in this case, you can show that X1 or Xn is a minimal sufficient statistic. Now if X1, Xn is minimal sufficient, any one-to-one function of X1, Xn is minimal sufficient. So Xn minus X1 and X1 plus Xn by 2 is also minimal sufficient because they two are one-to-one function. Why? Because if you know X1, Xn, you know Xn minus X1 and X1 plus Xn by 2. Now, if you know Xn minus X1 and X1 plus Xn by 2, by solving two simultaneous equations, you can get what the exact value of X1 and Xn is. So knowing this, T1, you know T2, knowing T2, you know T1. So if T1 is minimal sufficient, this is also minimal sufficient. But note that this is a location family. And just now we have shown that in the location family, Xn minus X1 is ancillary. In fact, any statistic which satisfies V of X1 plus C, Xn plus C, V of X1, X2, Xn, C would be ancillary. And this statistic satisfies this. So this is ancillary. So note that here minimal sufficient statistic has a component which is ancillary. This may sound slightly paradoxical, but I'll explain why this may happen. On one point, I'm saying that Xn minus X1 has no information about theta. I'm saying once you use with X1 plus Xn by 2, you note that X1 plus Xn by 2 alone is not sufficient. Alone is not sufficient. Forget about minimal sufficient. You can use it because this is minimal sufficient, and minimal sufficient statistic has to be a function of every other statistic. So if it was sufficient, I should be able to get T2x from this. But I cannot get T2x from this, so it is not minimal sufficient. It is not even sufficient. But when I use this statistic with something else, it becomes a minimal sufficient statistic. When I use with an ancillary statistic, it becomes a minimal sufficient statistic. So this example illustrates that as such, ancillary statistic may not contain any information about theta, but when it is used with some other statistic, it may contain a lot of relevant information. So in this case, ancillary statistic is an important component of the minimal sufficient statistic. Certainly, the ancillary statistic and the minimal sufficient statistic are not independent. See, your heuristics may suggest that since one contains all the information about theta, other does not contain any information about theta, the two should be independent. That doesn't happen over here because x1 plus xn by 2 and xn minus x1 are not independent in uniform theta, theta plus 1. That can be easily solved. And why this is happening? Because you see, when xn minus x1 was used alone, its distribution does not depend on theta. But the joint distribution of xn minus x1 and x1 plus xn by 2 might have a correlation because they may be dependent. When they are dependent, that unknown theta may come to their correlation. So their dependence may contain information about theta. Because xn minus x1 only considers the marginal distribution of xn minus x1. And what I know is marginally, xn minus x1 has a distribution which does not depend on theta. But with some other statistic, it may have a joint distribution which may depend on theta. So which may contain information about theta. And that is what exactly is happening over here. So a take-home lesson from this would be, once the ancillary statistic alone does not contain any information about theta. But when it is used in conjunction with some other statistic, it may contain a lot of information. So this is what this remark says. Although an ancillary statistic by itself contains no information. So as ancillary statistic by itself contains no information about the parameter theta. But when it is used in conjunction with other statistics, sometimes does contain valuable information. Let us consider one other example to illustrate this point. Suppose x1, x2, xn are IID random variables with common PMF f theta x, which takes value 1 by 3, same probability for each of the point at theta, theta plus 1, and theta plus 2, where theta is an integer. Now, in this case, T1x, x1, x2 is minimal sufficient because here, if you look at f theta x1, x2, this equals 1 by 9. I know x can take only integer values because x takes value theta, theta plus 1, and theta plus 2. So what you know is each xi is bigger than theta. So x1 is bigger than or equal to theta. Each xi is less than or equal to theta plus 2. So xn less than or equal to theta plus 2. And your xi you take, only take integer values. Xi 2, 1, 2, and sorry, 0 plus minus 1. So let me call that as set of I. And 0 otherwise. Now this can always be written as 1 by 9 can come. Indicator theta lies between x1 and xn minus 2. x1 and xn minus 2 of theta into hx. What is hx? Hx is indicator function of that each xi is an integer. So product I is equal to 1 to n, that integer xi is an integer. So by factorization theorem, you can easily show that x1 and xn is minimal sufficient. If x1 and xn is minimal sufficient, any one-to-one function of this would be minimal sufficient. x2 minus x1 plus x2 by 2 would be minimal sufficient. Now, this clearly belongs to location family because f theta x can be written as f of x minus theta, because your x minus theta takes value, yeah, x minus theta takes value 0, 1, and 2, each with probability 1/3. So where what is f? F takes value 1/3 if x is 0, 1, and 2, and 0 otherwise. It is a location family. So x2 minus x1 would be ancillary. V of x1 plus c, xn plus c would be same as v of x1, x2, xn. So x2 minus x1 is ancillary for theta. So although T1x, T11x, we can call this as x2 minus x1 as T1x is ancillary, it gives information about theta because together they are minimal sufficient. X1 plus x2 by 2 alone is not sufficient. To see again very concretely how this is happening is, consider a sample point T11 and T12 where I know that T12 is an integer. T12 is an integer, that means x1 plus x2 by 2 is an integer. Now, if x1 plus x2 by 2 is an integer, what does that say? This implies that your x1 and x2 values can be, if x1 plus x2 is even, x1 plus x2 is even, either both are taking the same values, x1 and x2. So theta, theta, or theta, theta plus 1, theta plus 1, theta plus 1, or theta plus 2, theta plus 2. Because T12, which is x1 plus x2 by 2, is given to be an integer. That means x1 plus x2 has to be an odd even number. That means either they are same, theta is an integer, or it could be theta and theta plus 2 also. What does this information say? This says that your x1 and x2 could be theta. So for example, this says that x1 can be theta, theta plus 1, or theta plus 2. So basically this says that your T12, the values which it can take is theta, theta plus 1, or theta plus 2. These are the values one can take. So that means from just the value of T12, what we can conclude is theta is equal to T12, or theta is T12 minus 1, or theta is T12 minus 2. So if just the value of T12 is given, I cannot determine theta precisely because theta can be either T12 or T12 minus 1 or T12 minus 2 once you are given that x1 plus x2 by 2 is T1. Now suppose that along with this T12 is equal to 2, I'm also given, there's a misprint over here, T11 as m. T11 is m and T12 is 2. What does that mean? T11 is m, that means x2 minus x1 is m. And x2 plus x1 by 2 is 2. So that means x2 plus x1 this you can write down as 2m, right? So T11 is given to be 2m, which is x2 minus, no, this is given to be 2 only. This is okay. T11 is given to be 2 and T12 is given to be, this is okay, T12 this is okay, T11 has 2. And suppose T11 is given to be 2 and T11 is given to be m. Or x2, yeah. Then basically you're saying that x2 minus x1 is 2 and x2 plus x1 by 2 is m, so x2 plus x1 is 2. What does that give? I subtract the 2. 2x1 becomes 2, and so x1 is m minus 1, and x2 is m plus 1. So with this, I get x1 as m minus 1 and x2 as m plus 1. But you know that whenever you are getting a sample, the maximum difference between the sample could be 2. That is when one of them is taking value theta and the other is taking value theta plus 2. Now in this case, I have observed that my theta is x1 is m minus 1 and x2 is m plus 1. So that means the smallest value which one can take is m minus. So that means theta has to be m minus 1. And so that means x1 is same as theta and x2 is same as theta plus 1, because any xi can take value theta, theta plus 1 and theta plus 2 only. And if x1 is m minus 1 and x2 is m plus 2, that means x1 is theta and this is same as theta plus 2. So that means theta is same as m minus 1 is the smallest one. So note that alone T11, T12 did not have any information about theta, but the moment I add x2 minus x1, it gives me precisely the value of theta. The knowledge about the ancillary statistic x2 minus x1 has increased our knowledge about theta. Again, emphasizing the point that as such, ancillary statistic may not contain any information about theta, but when it is combined with some other statistic, it may contain a lot of valuable information. Now, our intuition suggests that minimal sufficient statistic and ancillary statistic should be independent. Why? Because one contains all the information about theta, the other does not contain any information about theta. In many situations, this is correct. But in many situations, this may not be correct, as we saw in the last example, and example of uniform theta, theta plus 1. But before that, let us consider example of a Cosy distribution, x1, x2, xn be IID, with a common Cosy distribution. Now, in this case, one can show that the minimal sufficient statistic is the order statistic. So there is a very little reduction in data. From n dimension, you only go to n dimension. And reduction in the sense that you don't have to know the full of x1, x2, xn. You just need to know the ordered values. So this is minimal sufficient. I consider another statistic which is n minus 1 dimensional, which is a function of this statistic, which is xn minus x1 and xn minus xn minus 1. So here you can see that v of x1 plus c. Cosy is a location family. Any statistic which satisfies v of x1 plus c, xn plus c, equal to v of x1 xn, for every c should be ancillary. And that is what is happening over here, because maximum would get converted to maximum plus c, minimum would get converted to maximum. In fact, each of the order statistics will just get translated by c. Then you translate each of the observations by c. So because of the difference, that c would get cancelled. So this statistic satisfies this, so it would be ancillary. So here Tx is minimal sufficient and V is ancillary. Is xn minus x1 and xn minus xn minus 1. Now, let me illustrate situations where an ancillary statistic and a minimal sufficient statistic to begin with, or for that matter of fact, any ancillary statistic and any sufficient to be. That leads to the notion of completeness. To motivate the study of this notion, let us look at again the example of a Cosy family. And let us look at another example, which is normal family. So if it's x1, x2, xn is normal theta 1, I know the minimal sufficient statistic is x bar. So reduction in data is substantial from n-dimensional data, x1, x2, xn, you only want to x bar, and you're saying it's enough to consider only x bar. But in Cosy family, the maximum from n dimension, you can go to only n dimension, and that too in terms of order statistics. So I see these two examples give me two extreme cases of reduction in data. The examples of Cosy family and normal family, so that the degree of reduction that can be achieved through sufficiency is extremely variable. So the question is, what are the situations where sufficiency provides substantial reduction of data? Certainly, the amount of reduction of data by a minimal sufficient statistic seems to be related to the amount of ancillary information it contains. So what we have seen is a sufficient statistic may still contain an ancillary information. For example, here x1, x2, xn was minimal sufficient. But what I saw is, if I consider some function of this xn minus x1 and xn minus xn minus x1, that has no information about theta, that is ancillary. So in certain sense, this x1, x2, xn, it looks like has some ancillary information because a function of this does not have any information about theta. So if your statistic is such that it has no ancillary information, all the ancillary information has been gotten rid of, then I can say such a statistics gives me maximum reduction in data. So that leads to the concept of ancillary completeness. So an ancillary statistic by itself contains no information about f or theta, but minimal sufficient statistic may still contain much ancillary information. Example, in the Cosy family, although x1, x2, xn was minimal sufficient, a function of that is ancillary, has no information about theta in the sense that its distribution does not depend on theta. So although x1, x2, xn was minimal sufficient, a function of this has an ancillary information. So a sufficient statistic T appears to be more successful in reducing the data if no non-constant function of T is ancillary. For example, here, a function of the minimal sufficient statistic was ancillary. If no constant function of sufficient statistic is ancillary, then we can say that we have succeeded in reducing the data substantially. That would be possibly going too far. So what I need is a concept of, or a notion of first order ancillary. What does that mean is? That means if expected value of psi t is c, that means if there is some function psi such that expected psi t is c, then this psi t has to be constant. It cannot depend on theta. So T, I would have said that T was no constant function of T is ancillary. That means the distribution of psi T does not depend on theta. No non-constant, no constant. So that means if it depends on theta, it has to be a constant function. That has been slightly diluted in the sense what I'm saying is if expected value of any non-constant function is a constant, does not depend on theta, that means that function itself has to be constant. So that means no constant function can have expected value. No non-constant function can have expected value, which is it has to depend on theta. So that means you've gotten rid of all the ancillary information.
So this is not clear to me.
Yeah.
Can you please repeat?
So just look at an ancillary statistic by itself contains no information about theta. But minimal sufficient statistic may still contain much ancillary information, as we saw in the Cosy family. X1, X2, Xn order statistic was minimal sufficient, but when I consider its function, it is ancillary. So that means your X1, X2, Xn itself was considered hiding some ancillary information, because I could find a function of X1, X2, Xn. This distribution does not depend on theta. This suggests that a sufficient statistic will appear to be most successful in reducing the data if no non-constant function of this is ancillary. What does that mean is, if psi t is equal to C, if psi t is ancillary, that should imply that psi t is constant. Probability psi t is equal to C with probability 1. That is what it says. So what it suggests is, a sufficient statistic would look like to be very successful in reducing the data if no non-constant function of this is ancillary, because here this was a non-constant function and it is ancillary, and that gives the information that this X1, X2, Xn has some still ancillary information, because I could find a function of it which was ancillary. So this leads us to believe that a sufficient statistic would be most successful in reducing the data if no constant function, non-constant function of t is ancillary.
Okay, sir, got it.
If psi t is ancillary, then psi t has to be constant, because no non-constant function can be ancillary. So I'm saying this, I dilute this little bit. What it says is, if expected value of psi t does not depend on theta, that should imply that psi t is C with probability 1. So if you have any statistic of this type, that looks like is very successful in reducing the data. And that leads to this definition: a family of PDFs or PMFs is said to be complete. I also introduced the definition of a boundedly complete if for every function psi, so this constant I can consume with psi t itself, right? So that means absolute psi t minus c is equal to 0. That means psi t minus c should be 0. So I can write down the definition of a completeness in the following form: a family of PDFs f theta theta belonging to theta is said to be complete or boundedly complete if for any function in the case of completeness and bounded function in the case of boundedly completeness, with expected value of psi x equal to 0 should imply that psi x is 0 with probability 1. And that is motivated through this definition. So certainly, if any statistics which is complete, I would expect, if it is also sufficient, I would expect that it has succeeded in reducing the data maximally. So I would expect such a statistic to be minimal sufficient. So this leads us to believe that any complete and sufficient statistics will be minimal sufficient, and we'll show that later on. However, before that, just let me make this remark: every complete family is boundedly complete, because if it happens for all functions, it would happen for a bounded functions also. So every complete family is boundedly complete. A boundedly complete family may not be complete. And here is an example I have written down. I'll give this as a homework problem. Let X be a family with random variable f theta x, theta f theta x is equal to theta if x equal to -1, 1 by theta square, theta to the power x is so on, 0 otherwise, then f theta is boundedly complete but not complete. I can show you, give you a hint a little bit over there, but before that, let me see. You should note the fact that a polynomial can have only n roots. A polynomial can have n roots. So if a polynomial which depends on theta, so let us say a polynomial theta, is 0 for every theta in an interval. For every theta in an interval. Polynomial of finite degree in theta. For example, it could be theta square plus theta plus 1. 2 theta square plus theta plus 1, theta to the power n plus theta to the power 5 plus theta cube, and so on. So it is any polynomial of finite degree. This is 0 for every theta belonging to I. What does that mean? Can anyone tell? If a polynomial is 0 for every theta in I, what would that mean? Can that happen? You see, a polynomial can have at the most n roots. If a polynomial is of degree n, which is given over where it is a finite degree, so it can have at the most n roots. But I am given that it is having a root belonging to everything in an interval. So that means it has infinitely many roots. That can happen only when the polynomial itself is 0. Polynomial is 0 means coefficients of p theta are 0. Coefficients of theta to the power n in p theta are 0. So that is a one fact we'll be using. The other fact is, if you have a power series, an theta to the power n, this is 0 for every theta in an interval. What would that mean? You know that two power series matches, if two power series match on an interval, their coefficients have to be same. So if a power series vanishes in an interval, that should imply that each an is same. So using these two facts, one can show that this family is boundedly complete but not complete, because what you have to show is, if for boundedly complete, you have to show that for any bounded function, expected value of psi x is 0 for every theta belonging to 0, 1. That should imply psi x equal to 0 with probability 1. In the case of boundedly complete, you take psi to be boundedly complete. In case of completeness, you take any psi. Now, this certainly implies, if I look at this over here, expected value psi x would be what? X takes value theta, x takes value minus 1, would be theta. Thus, it can take any value x from 0 to infinity. Psi of x into 1 minus theta square theta x. This is equal to 0. With theta between 0 and 1. Now, if you want 1 minus theta to the power minus 2, I can subtract both the sides. So that means x equal to 0 to infinity. Psi x theta to the power x is same as, this goes over here. So psi of minus 1 theta into 1 minus theta to the power minus 2. Now, this can be written as a power series in theta, because 1 minus theta to the power minus 2 can be expanded in power series, which is 1 plus 2 theta plus 3 theta square and so on. So both the sides you get a power series, they match, so their coefficients match. I can get the values of psi x. And then you can prove this. That this is an example where family is boundedly complete, but not complete. Let me just give a definition of a statistic being complete, and then I would just stop. Or let me just stop over. So this is end of today's lecture. Those of you who have any doubts may stay back, others may leave. Okay, if there are no questions, I still see 5 participants. Any one of you have any doubt? Vidista, Rosen, Sandeep, Santanu. Does anyone has any doubt? Or Rosen? Rosen, do you have any doubt? Seems to have already left the meeting. That's not fair. Okay, so let me call off the meeting for today.